Dear students, in this video, we will discuss examples on monotonicity and convergence with the help of boundedness and monotonicity. Fine. So here, first we are taking the examples on monotonicity. So here we have taken five examples. Prove that the following sequences are monotonic. That means either they are monotonically increasing or decreasing. Here first example is an is equals to 1 by 2 plus 1 by 2 square plus 1 by 2 cube and so on up to 1 by 2 raised to the power n. Second example is 1 by n plus 1 by n plus 1 plus 1 by n plus 2 and so on plus 1 by 2n minus 1. Third example is 3n plus 7 divided by 4n plus 8. In the fourth example, an is 1 plus 1 by n raised to the power n. And in the last example, we have a recurrence relation where an is square root of 2 plus an minus 1 and n is greater than equal to 2. To start the process, a1 is given to you 1. So these are the five examples. Now we will take one by one. First example is 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus 1 by 2 raised to the power n. Now to check the monotonicity, we have already a condition which says that an plus 1 should be greater than equal to an for all n belongs to n. Then this is monotonically increasing. If an plus 1 is less than equals to an for all n belongs to n, then this is monotonically decreasing. So this is the condition. So for this we have to find out the difference between an plus 1 and an. If this difference is positive, then increasing. If this difference is negative, then decreasing. Fine. So this is the approach. So here an is already given to you. Find out an plus 1. So which is nothing but according to this formula 1.2 plus 1.2 square plus 1 by 2 cube plus 1 by 2 raised to the power n plus 1 by 2 raised to the power n plus 1. Take the difference of these two. So these terms will be cancelled out. Only left term is this. So which is nothing but a positive term for any n, because n is a natural number. That's why an plus 1 will be greater than an, and so monotonically increasing, and hence monotonic. Second, in the second example, an is 1 by n, 1 by n plus 1, 1 by n plus 2 plus 1 by 2n minus 1. So an plus 1 will be n plus 1, n plus 2, n plus 3, 2 into n plus 1 minus 1. So this will be nothing but 2n plus 1. After substituting n by n plus 1, we get this term here. So now take the difference. When you take the difference, so these terms will be cancelled out. So only the left terms will be these. So here 1 by 2n plus 1 by 2n plus 1 minus 1 by n. So the only left terms are these. Fine. So these are the left terms. Now simplify. So we get a negative value which is less than 0. And that's why an plus 1 is less than an. So monotonically decreasing, and hence monotonic. Fine. Now next example is this. An is 3n plus 7 divided by 4n plus 8. Similarly, an plus 1 will be just replace n by n plus 1 here. So we get this term. Find out the difference, which is nothing but minus 1 by 4 into n plus 3 into n plus 2, which is less than 0. That's why monotonically decreasing. Now next example is this. An is 1 plus 1 by n raised to the power n. Just expand this with the help of binomial. So we get 1 plus n, 1 by n plus n into n minus 1, because we know that this term is nc1 and its value will be n. So n 1 by n. N into n minus 1 by factorial 2, 1 by n square and so on. And last term will be ncn. When you simplify this, so we get n into n minus 1 into n minus 2 up to 1 divided by factorial n, 1 by n raised to the power n. Fine. Now we will divide this term. First term is as it is. In the second term, n into 1 by n. Simplify, so we get 1. In the next term, we are having this type of term, n into n minus 1 by factorial 2 into 1 by n square. So we can rewrite this as 1 by factorial 2 n upon n into n minus 1 by n. This is cancel out. So we get 1 by factorial 2 into 1 minus 1 by n. This is written here. Similarly, in the next term, what we get? N into n minus 1 into n minus 2 divided by factorial 3 into 1 by n cube. So again, divide this divide n cube into three parts. One is n by n, another one is n minus 1 by n, another one is n minus 2 by n. Separate these, so this is cancel out. So 1 by factorial 3. Now divide this, so 1 minus this, 1 minus 2 by n, and this is written here. Similarly, rest of the terms. So last term will be in the same way, can be written as 1 by factorial n, 1 minus 1 by n, 1 minus 2 by n, 1 minus n minus 1 by n. Fine. So this is, now this is an. Now an plus 1 will be just replace n by n plus 1. So we get this term. Now take the difference. So when you are taking the difference, so we will cancel out or compare the term by term. That means we will compare this term with this term. If this is, for example, if this term is positive or greater than this term. Similarly, if this term is greater than the second order term, and so on. So we can say that an plus 1 will be greater than an. Fine. So we will compare term by term. So for this we are using this. Since we know that n plus 1 is greater than n, so just take the reciprocal. So 1 by n plus 1 is less than 1 by n. Now multiply by positive constant k by n plus 1, where k is a natural number, 1 to n. Why we have multiplying this? Because we are having term like this, 1 minus 2 by n plus 1, 1 minus 3 by n plus 1, 1 minus 2 by n. So this will be nothing but a k type number. So that's why we have multiplied this. Now multiply by minus sign. So minus k upon n plus 1 is greater than minus k by n. After now adding 1, so we are getting this. So if you compare, this type of term is always greater than this. That means this type of term is always greater than this type of term. Similarly, this term is greater than this term is greater than this term, and that's why this type of term, product, this product is greater than this type of product. And hence we can say that when each term is greater than, that's why an plus 1 will be greater than an, and so monotonically increasing. Fine. So an, this sequence is monotonically increasing. Now the last example here, a1 is 1, a2. Just put in the recurrence relation, this recurrence relation, put n is equals to 2. So we get a2 is equals to square root of 2 plus a1, and we have a1 is equal to 1, so we get this root. So a2 is greater than a1. So now we will prove this, the monotonicity, with the help of induction. So for n is equals to 2, we have already get the result. Suppose an is greater than an minus 1. Now we will prove the result for n plus 1. So for n plus 1, just adding 2 here. So 2 plus an is greater than 2 plus an minus 1. Take the square root of both sides, but this is nothing but, according to the recurrence relation, an plus 1. This will be an. So again we can say that this sequence is greater than that. That's why an is monotonically increasing. So this is the examples related to monotonicity. Now here we are taking we will have some examples on convergence, and we will establish the convergence with the help of monotonicity and boundedness. Because we have theorems which says that if sequence is monotonically increasing and bounded, then converges to its least upper bound. Similarly, if a sequence is monotonically decreasing and bounded below by some number, then the sequence converges to its greatest lower bound. So we will utilize those theorems here. So let us see. We have having again 5 examples. An is n plus 1 by n, an is n by n square plus 1, an is this 1 plus n cube plus 1 by 1 plus 1 by 3, sorry, 1 plus 1 by 3 plus 1 by 3 square, 1 plus 3 by raised to the, an is 1 plus 1 by n raised to the power n, and fifth is a recurrence relation. Fine. So here an is n plus 1 by n, we can write down this as this. An plus 1 will be this. If you find out the difference, so we get this term which is less than 0, and that's why this is monotonically decreasing. Now to show the convergence, we have to only prove that the sequence is bounded above. So since an is 1 plus 1 by n, this is greater than 1. So this sequence is, sorry, here we have shown that this sequence is bounded monotonically decreasing. So we have to prove that this sequence should be bounded below. So an is 1 plus 1 by n, that's why this is greater than 1, and hence this is valid for all n. So sequence is bounded below. So obviously this sequence will be a convergent sequence. Now find out the limit. So limit of n tending to infinite an is equals to limit n tending to infinite. What is an? An is n plus 1 by n. Simplify this, so we get the limit, the value of the limit. So this is the procedure. Similarly, the second example here, an is n by n square plus 1. An plus 1 will be then n plus 1 upon n plus 1 whole square plus 1. Take the difference of these two. After simplification, we get this value, which is negative value. So again, this is monotonically decreasing sequence. So we have to show that the sequence is this sequence is bounded below. So since an is n by n square plus 1, so this will be greater than 0 for all n, because n is natural number. So this is, and hence we can say that this sequence is bounded below. Now to find out the limit, just take the limit n tending to infinite an. So limit n tending to infinite and an is n by n square plus 1. So just divide by n square. The numerator and denominator is divided by n square. So we get 1 by n, 1 plus 1 by n square. Apply the limit, so we get 0. So that's why the limit will be 0 of this sequence. In the third example, an is 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 raised to the power n. A geometric progression. Similarly, an plus 1 will be 1 plus 1 by 3 plus 1 by 3 square, 1 by 3 raised to the power n plus 1 by 3 raised to the power n plus 1. Find out the difference. This difference is 1 by 3 raised to the power n plus 1, which is a positive quantity for all n, and hence sequence is monotonically increasing. Now to show the convergence, we have to prove that the sequence is bounded above. So since an is this, a geometric progression in which n plus 1 terms are involved, here a1 first term is 1 and ratio is 1 by 3. So with the help of the formula, we applied the formula and find out the sum of this geometric progression. So after simplification, we get this 3 by 2, 1 minus 1 by 3 raised to the power n plus 1. Multiply this 3 by 2, so we get this result. And you can see that this quantity is positive. This is 3 by 2 minus something. So that's why this value will be obviously less than 3 by 2. So that's why an is bounded above by 3 by 2. And hence this is monotonically increasing and bounded above, so converges. Now to find out the limit an is equals to limit n tending to infinite. So an, after simplification, an is nothing but this type of term or this type of term. So suppose we are using this one. So 3 by 2, 1 minus 1 by 3 raised to the power n plus 1. Apply the limit. So 3 by 2, 1 minus 0. This is 3 by 2. So the limit is 3 by 2. Now the fourth example. Fourth example we have already taken in when we are discussing this boundedness and monotonicity. So an is 1 plus 1 by n raised to the power n. We have already proved that the sequence is bounded by 2 and 3. The value will be in between 2 and 3. So this sequence is bounded. Monotonically increasing, we have already proved in previous example. So this is monotonically increasing and bounded. That's why a convergent sequence. Now to find out the limit n tending to infinite, 1 plus 1 by n raised to the power n. To find out the limit, we will use this formula. Limit n tending to infinite, 1 plus x by n raised to the power n is nothing but e raised to the power x. In our case, x is 1. So e raised to the power x, that means 1 is equals to e. So this is the value of the sequence, the limit of the sequence. Now in the last example. Now whenever we are having this type of recurrence relation, so first we will show that the sequence is either monotonically increasing or decreasing as per the given sequence. So here a1 is root 7, then find out a2. a2 is nothing but 7 plus a1, but a1 is root 7, so this value is root 7 plus square root of 7. This is greater than obviously root 7, and root 7 is a1. So a2 is greater than a1. Now suppose an is greater than an minus 1, because we are proving the monotonicity with the help of induction. So first is our Now suppose an is greater than an minus 1. Now we will prove that an plus 1 is greater than an. So to show that suppose an is greater than an minus 1, take adding 7 both sides. So 7 plus an is greater than 7 plus an minus 1, taking the square root of, so but this is nothing but an plus 1, which is, and this term is an, so an plus 1 is greater than an and hence monotonically increasing. Now sequence is monotonically increasing. Now to show the convergence, what you have to prove? You have to prove that sequence is bounded above. So since a1 is square root of 7 and we know that square root of 7 is less than 7, because we have to find out only a upper bound. So in this case, upper bound, suppose you have assumed as 7, and suppose, so we will again find out the upper bound with the help of mathematical induction. Here a1 is less than 7. Suppose an is less than 7, then we will show that an plus 1 is also less than 7. So 7, just adding both sides 7, so 7 plus an is less than 14. So now taking the square root, 7 plus an is less than square root of 14, and we know that square root of 14 is also less than 7. That's why an plus 1 is less than 7, and hence we can say that an is always less than 7 with the help of mathematical induction. So bounded above. So now we have proved that sequence is monotonically increasing and bounded above by 7. That's why it converges. Now to find out the limit, so we know that, suppose, because in this case this is not easy to find out the limit, so that's why we will apply this approach. What, suppose limit n tending to infinite an is L. So now our target is to find out L. Now if limit n tending to infinite an is L, then obviously limit of n tending to infinite an plus 1 is also L. The value of this limit and this limit both will be L, because in a sequence if we remove some terms or add some terms, then limit will not disturb, limit will be as it is. So that's why, so an plus 1 is equals to square root of 7 plus an, squaring both sides, so we get this. Now apply the limit, taking the limit, and this is according to this is L square. Here 7 plus L, we are having a quadratic equation. Solve this equation, so we get two roots, 1 plus minus square root of 29 by 2. One root is positive, another one is negative, but as per the given relation here all the terms are positive, so that's why limit will also be positive. Limit cannot be negative for a positive sequence. That's why negative root, which is 1 minus square root of 29 by 2, so we can neglect this root, and only possibility of limit will be 1 plus square root of 29 by 2. This is the value of the limit for this sequence. Fine. So these are few examples. Now in the next video we will take the algebra of limits of the sequences. Thank you.